Yeah, so this is the, as I told you, the schedule or the program of the winter school. As I told you, actually I am opening this winter school. In few minutes, our school director will join us to say some words about this this winter school, and we have also a time for our academic partners, Kiel University, l'Aquila University, and Bucuresti University, to present briefly the program or what will be given on this master according to these universities. Okay. And after that, we will start the presentations scheduled on this winter school. So first of all, we will start by the presentation from Rono about high voltage electric architecture, as you can see here. The next presentation will be given by Neuville company from Germany, okay, about electric bike trailers control and power electronics. So this is the presentation that are scheduled on this on the morning of this day, okay, and we'll have a break, and at PM. So at 2:30 to half PM, we'll have a presentation from DG Power about multi-level power converters for electric propulsion systems and energy infrastructure. So this is the program of this first day. Okay. So tomorrow, second day of this winter school, we will have 3 presentations. The first one will be from P2C company or industry about challenges and opportunities for electronic control in battery electrical vehicles and hybrid electrical vehicles. Okay. Then the next presentation will be given by Daimler, Mercedes-Benz, about general strategy for electrification in automotive. Okay. So this is the morning program of this second day. And on PM, there is a presentation from Rono at 2:30 hours about battery management systems. So the third day of this winter school, the program of this third day, third day is shown here. Okay. So there is a 4th presentation. So first of all, we will start by giving a virtual visit of Renault Electric Engine bench at Centrale Nantes to the students. So this bench is designed on the according to the chair that we have with Rono about electric vehicle performances improvement. Then with this will give us on the morning the second presentation of on the morning, okay, about project autonomous driving electrical car developing of 2 OBU. Then on PM, so we will have a chair of power electronics at Kiel University. We will close this winter school by the presentation of Rono. So at PM of the third day about hybrid electrical vehicles. So here, just to say some words about the EPiCo master. As I told you, I will start this by presenting to you the consortium. So there is 4 academic partners, as we have seen. So we have Centrale Nantes, so our school, which is the coordinator, and we have the others, Union European partners. So as you can see here, UPB Bucuresti from Romania, l'Aquila from Italy, and Kiel from Germany. Okay, and also there is 3 associated academic partners. So ETS from Montreal in Canada, and Wuhan University from China, and Cinesta from Mexico. Okay. And of course, we have industrial partners that accepted to give a talk about electrical mobility issues. And again, thank you for our industrial partners to accept to give these talks to our students. So there is, as you can see here, Renault, Airbus, IAV, Daimler, Honda, P2C, Moody's, DigiPower, ECA Group, Techni, okay, GENNARO, and of course there is a possibility for other partners. For example, we have today the talk about Neuville, who is not official partner of this master, but we can see the possibility if Neuville is interested to be the official industrial partner of this master. Okay, and just here I recall the role of this industrial partners. Okay, so as you can see here, the main purpose is to support the master, as it is done today, and for this winter school, participation, of course, to training and schools, of course, and there is also possibility to participate to the master evolution, to join us for a discussion in order to see how to improve the content of this master about electric mobility issues. And also there is a possibility to propose internships to students and to enroll students on companies, on industries. Okay. So just here to say some words about the staff of the master. So there is a management office, as you can see here. And there is a program coordinator and local coordinators in each partner. Okay, and here just to say one word about this management office, I would like to thank a lot all persons of this management office, and particularly as you can see here, Marie-Pierre Pichout, who managed very well the organization of this first winter school of the master. Okay, so just here to see the coordinator. So mine's I am the principal coordinator of this master, and as I told you, in each partner there is a local coordinator. Okay, each academic partner. And here I will briefly present to you the mobility scheme and the academic program of this master. As you can see here, the program of studies tests 2 years. Okay, the program of study lasts 2 academic years, year 1 and year 2. Okay, which are split into 4 equally loaded semesters, as you can see here, S1, S2, S3, and S4. They are semesters, and EPiCo student mobility path will take in minimum, as you can see here, 2 Union European countries, okay, and possibility there is a possibility to have to take place in 3 Union European countries for the first S1, for the first 3 semesters, S1, S2, and S3. As you can see here, the first semester is done in Centrale Nantes. So all the students are here in Centrale Nantes, and then now on the second semester, the students will go to the 3 other partners, UPB, l'Aquila, and Kiel. And on the second semester, as you can see here, they will be involved on all the 4th academic partners, UPB, l'Aquila, Kiel, and Centrale Nantes. And for the 4th semester, EPiCo students may move to partner countries, okay? As you can see here, European academic partners, non-European academic partners, which are called associate academic partners, or they can also move to industrial partners, official and or not official, okay? So this is the master thesis, internships. So here, as you can see, there is the program, academic program of each semester in each partner. So as I told you, the first semester is done in Centrale Nantes, and this first semester is aimed to provide students with a solid background across the main areas of automatic control, as you can see here, control systems, and also electric vehicles. So there is some lectures about fundamentals of electrical vehicle systems and modeling, simulation of electrical vehicles. So the aim of the second semester, which is, as I told you, would take place on the 3 other academic partners, l'Aquila, Kiel, and Universitas, and UPB, Bucuresti. It's P here, sorry for the mistake. So the aim is to provide students with a solid background in electrical vehicles components. As you can see here, power electronics converters, electrical machines used in electrical vehicles, renewable energy and storage systems. And also there is some lectures about nonlinear control systems. So during the third semester, so more specialized courses or lectures are proposed. So the program of this semester, as you can see here, is based on the specific research of each partner institution. As you can see here in Bucharest, so this third semester will be more focused on energy storage systems. In Centrale Nantes, it will be focused more on control of electrical propulsion systems. In Kiel University, it will be on control in e-mobility, electrical mobility, and in l'Aquila, it will be about embedded systems and communications in e-mobility systems. Okay, and the last semester of this master, so which is dedicated to master thesis or internship. So just to give you some elements about this, so there is 5 to 6 months of duration of this master thesis. So the max duration is 26 weeks. This master thesis can start, so for industrial partners and formation, this master thesis can start mid to late February, must be finished before the end of August 31. Okay, so the research topics of this master thesis can be supervised and located in R&D department of an industrial institution, can be within institution or industry. Okay. Yeah. Yeah, maybe just to say some words about the first intake of our students, which are for our students who are now connected and following this first winter school of the master. So we received for this first intake, I think, Marie-Pierre, if I'm wrong, correct me, we received maybe more than 600 applications for this first intake, and we enrolled 21 students, okay, for this first intake. And this is the origin of students. And as you can see here, we have 6 students from India, 3 students from Mexico, 1 student from Spain, Kosovo, Turkey, Russia, China, Egypt, Brazil, Argentina, Chile, Ecuador, Colombia. So just to say the different origin of students, and this is the main purpose of this Erasmus Mundus master program, is to enroll the best level of students and with different origins. So good morning, Mr. AVRILLIER. So yeah, thank you very much to be here in order to say some words about this first winter school about electrical vehicle propulsion and its control. So the students are very happy, and also our industrial partners are very, very interested by this this winter school and by your talk.
Thank you very much. Thank you very much, dear partners, colleagues, students, alumni, ladies and gentlemen. I'm very happy to open this 2021 edition, first edition of the E-PiCo Winter School. The international visibility and collaborations for training and research is one of the main objectives of Centrale Nantes. We have 178 academic partners all over the world, and 43% of our students are international students on our campus, representing more than 80 different nationalities. We are very happy to welcome you to this winter school, because EPiCo is very important Erasmus Mundus program for us, with 4 partner institutions and also with our industrial partners that we are very proud to work with and to study with you for these 3 days. And also to say that EPiCo is very important to us because we are talking about e-mobility and the development of electronic vehicles together with academic institutions and its industrial partners. And this is very important for us for the training of our master students and also for the future of mobility and of our collaborations with industrial partners. And I wish you all 3 days of very interesting discussions. Thank you very much.
So thank you very much, Jean-Baptiste, for this intervention.
Still, yeah. I hope. Okay. Welcome from Kiel. We are happy to be part of this great program, EPiCo. So we have prepared a few slides just showing you some features from Kiel and how we are going to structure the studies there. So my name is Thomas Meurer. I'm program manager and chair of the examination board for EPiCo at Kiel. Some brief facts, so not in too many details. The university is about 350 years old now. You see, it was founded by Christian-Albrechst. This is why the university is also called Christian-Albrechst-Universität, which is the CAU acronym that you find sometimes. So it's the only fully fledged university in Schleswig-Holstein, about 27,000 students, over 2,000 scientists and scholars. We are organized in 8 faculties. We have a bunch of priority research areas, which, of course, as we are located far north in Germany at the Baltic Sea, it's marine science and life science. There's also societal issues, and also nanosurface and interface sciences is one of the key areas. There are 2 clusters of excellence. This is a funded program in German from the German government, very competitive, and similarly also collaborative research centers, which are also similarly competitive. With 2 of them at the Faculty of Engineering. One is about magnetoelectric sensors, and there is a very new one which is about neurotronics, which is about neuromorphic devices and also learning in hardware and so forth. So nevertheless, Kiel is not only science, but also leisure. So there's 2 impressions from Kiel. If you just travel a little bit north to the beaches, I mean, there are very nice places where you can go to. So there is also lots of nice features that you can participate and join during the summertime in Kiel. So why are we part of this EPiCo program? So of course, EPiCo addresses, as was mentioned before, very important issues, and Schleswig-Holstein is in Germany one of the national pioneers in renewable energy production, so that EPiCo very nicely integrates into the research as well as the industrial environment here. Energy, you saw some of the priority research areas, but energy is also one of the possible new research areas that Kiel might focus on. There's lots of knowledge in different topics, from power electronics over control to production storage, and which is also mapped in terms of university courses. And also during the certification, we figured out that also our local students are very interested in this program. So there was very positive feedback from the current students. And it also strengthens nicely some of the larger scale research activities on e-mobility. And I would like to pick out one of them, which is what is called Clean Autonomous Public Transport in Kiel, kept in Kiel or kept currently, which is about generating a sustainable integrated mobility chain, dealing with autonomous, a lot of autonomy in the sense of, as you see on the top left, ferry operation. So there is a ferry operation on the Kiel Bay, and we are interested very much in, on the one hand, making this autonomous, but also integrating new propulsion concepts, fuel cells, e-mobility, and so forth. The same holds true for buses. It's for pedestrian operation, car, individual mobility, electric car fleets, and so forth. So there are many things that pop up. And the nice thing is that both industry, academia, and also the government is involved there, and they're all working to push this forward. To become a little bit more concrete concerning EPiCo, as you have the option to move to Kiel in semester 2 or semester 3, let me just mention a few of the modules that we offer. So semester 2 is, as you see here, about power electronics, renewable energy, as well as advanced courses in control. You also have the option to take an elective module, or you should take one. There is a short list that you find on the bottom part of the slide. And also you're supposed to take part in a German language course, which is important to get along locally. Moreover, for semester 3, we are following basically 2 tracks. So we offer 2 directions. So on the one hand side, if you're interested in focusing more on the control part of, let's say, complex dynamical systems, then we have a bunch of modules that we offer there at a master level, starting from optimization over rigid body dynamics, applying also the control in the laboratory, plus elective modules that you can take part in, which also start, as you see down here, from signal processing over modeling, image processing, which is interesting in autonomy or embedded real-time systems. And the second track is going to focus on power electronic drive technologies. As you see here, it starts from modeling from power electronic converters entering the grid, also evaluating the concepts that you learn in the modules in the corresponding laboratory, plus elective modules. And of course, you can also interchange a little bit between these modules and these directions. Also, and last but not least, if you're coming to Kiel, you will see in the next years that the campus is going to change a lot at the Faculty of Engineering. So there's lots of construction going on. It has started already. So there will be new buildings, lecturing building will be built up, a new one, and there will also be a new, what is called Center for Network Systems, where also research groups will be facilitated with lots of workspaces now. So the campus is going to change. If you will see it basically now or in the second semester and in the near future. And also, of course, EPiCo is about people. So we are also a team working at Kiel. Besides me, it's Professor Marco Lisere, who is going to give a talk, I think, on Wednesday, who is vice chair of the examination board, Kirsten Scholz, who is the local coordinator, she's also around, and Felix Heute, who is assisting us in organizational issues. So you also see the website. It's a lengthy URL. So basically just use Google on other search engines and search for EPiCo and Kiel, and you will directly hit this link. All right, that's it from my side. So if there are questions, don't hesitate to ask them or ask me. Thanks.
Yeah, thank you, Thomas, for this presentation. Okay, now we can switch to the to l'Aquila or Bucharest program presentation. So Stefano, are you ready to present l'Aquila?
What I can say is that the main subject in l'Aquila is about control. I would like to correct you a little bit, Malek, because you said that the focus is also on interconnected vehicles, which is not the subject. The main subject will be the control of electric vehicles. And indeed, we have in the second semester more or less the same topics, the same courses that are in all the three universities, in Kiel, Bucharest, and in l'Aquila, meaning nonlinear control, hard system control and simulations. And then we have common topics like power electronic converters, electronic machines, and renewable energy and storage systems. In the third semester, we have more focus, as I said, on control, with some courses about advanced control systems, systems identification and data analysis, embedded systems, optimization models, and algorithms. And the University of l'Aquila is, let's say, medium-sized university in which the student can find a very personal contact with professors and all the staff, and we can follow very closely students. This is an advantage, clearly. Our department also has some specific characteristics in the sense that we have all the components of what is the ICT information of the ICT technology. So we have computer science, we have informatics, we have telecommunications, and clearly control. Indeed, we have also components about mathematics, which is a part of our department. So the student can find a very, let's say, familiar and friend environment in which can develop his own activities. What else? I think that I've said more or less everything. I would just add that L'Aquila is very nice town, which is not far from Rome, which indeed is another interesting, let's say, additional advantage to be in L'Aquila, to be able to visit one of the most wonderful city in the world. And well, I welcome the students that will come in L'Aquila very soon, and I hope that also other students would like to come also to develop their thesis work. Thank you very much.
Okay, thank you, Stefano. I agree with you, Stefano. You are working a lot about control systems. You develop many theories about this. I agree with this, but you have also many applications on the field of electrical systems, and in particular, you have also skills on embedded systems, and communications in mobility systems issues and so on. So I think this aspect is more specialized on L'Aquila than others.
For sure. Thank you very much, Malik.
Yeah, you're
and
welcome.
If there are any questions, please address me these questions by mail or just send me a message in Skype or WhatsApp. Thank you.
Yeah, thank you again, Stefano. So maybe Octaviana or Dan, I think you are both connected. You hear me?
Well, I'm here. I'm Dan here. And
okay.
Well,
you will say some words about
yes, of course.
Program on UPB. Okay.
Okay.
And, University General. Okay. Thank you.
Well, now Politehnica University in Bucharest is the eldest university in the south of the country. It has almost 200 years old, and in this university there are 11 faculties. One of these faculties is the Faculty of Electronics, Telecommunications, and IT. In the faculty there are 4 departments: Applied Electronics, Telecommunications, and other 2. Anyhow, the person who are working in EPiCo are Octaviana Datcu, who belongs to the Department of Telecommunications, and Dan STOICHESCU, who is me, and I belong to the Applied Electronics. About our contribution to EPiCo. In the staff of EPiCo, we introduced professor, not only from our faculty, but also from the Faculty of Automotive and Computers and from Electrical Engineering. So in a way, the whole university is implied in preparing and working in EPiCo. Concerning some second semester, I could say that the first discipline, Power Electronics Converters, is given by a professor who worked over 30 years in this field, who has many papers and a serious experience. His name is Professor Constantin Radoi. The second discipline, electrical machines, is given by a professor in another faculty. Just I told you, we invited professors from also from other faculties. Mr. Tudoraki, he belongs to the faculty of electrical engineering, and he also has an experience of 15 years in this field. The third discipline, renewable energy and storage system, is given by Professor Adriana Florescu, who is full professor and who is specialist in power electronics, but also in renewable energy. He works in renewable energy for 7 or 8 years. Non-linear control systems is given by a professor from automatics and computers, Mr. Professor Lupu, who is also the vice dean of this faculty, a man of great experience, and I was very happy to have to invite him in our staff. Machine learning for autonomous systems is given by a young professor who studied not only in Bucharest, but also in Switzerland, and who has also, she's young, she's already associate professor, and her name is Ana Maria Radoi, and in this machine learning, she has an experience even from the days when she was a student. For the third semester, I can well mention that the professors who are giving these courses are also very excellent researchers in Politehnica, is Centrale on the whole for the whole university, and in this center there is a location department, not exactly, it is not called department, a laboratory where electrical machines are special studied. And in this laboratory, in research, are working 2 gentlemen who are giving courses just in this third semester. So their names are Mr. Alexander Vasile and Mr. Lucian Perișoară. And also I must mention here that we have also a professor from electrical engineering. Our experience in batteries is not exactly our experience, but let's say our possibilities in giving courses on electric batteries is enhanced by the presence of gentlemen from society, which is specialized just in manufacturing batteries. What could I mention to be interesting? In control, we have experience. I spoke about Mr. Lupu, who is a specialist. I told automation, but we could say also control systems. And in batteries, I mentioned, and in power electronics, also in our department, exactly in the department where I'm working, it is a strong experience. Well, when the students will come to us, they are welcome. we are prepared to support their instruction, their education, and not only, because we are ready also to present some elements from the Romanian culture and civilization, which is not very well known abroad. I stop here. I don't want to speak very much. If there are questions, I am ready to answer some. Well,
thank you, Dan. Yeah, for your presentation about the university, the program, and giving us details about the interveners of each lecture. Thank you so much. Okay, so now we can, I think, start the first presentation from Renault and from particularly Serge LOUDOT.
Yes, hello everybody. So maybe I can share my presentation. Hello everybody. Just I will have to show you a short introduction of what we are doing in Renault on automotive electric powertrains, and I will give you a short introduction of our strategy, why we are going into that direction of electrification. And after that, I will go to a deeper dive into the techniques, mainly to show you what are the specificities of introducing power electronics in powertrain, and what are these consequences for its control. Okay, so just to show you, so in Renault, we are a key player in battery electric vehicle. We have been pioneering mainly for the Zoe here, so 10 years ago. And right now, this is still a top-selling car. We sold more than 100,000 cars in 2020 in Europe. And we completed our lineup with here a Quid EV, and also with a hybrid or plug-in hybrid, so with a bigger battery and a battery charger. Of course, we are still going on, so there are some lineup and development. So this is a C segment and a smaller one facing to the past Renault 5 who has been revealed, and some other will come, but I cannot show you the picture right now. And of course, we are not alone. Almost all our competitors are going in the same way. So just to show you a brief and of course non-exhaustive of what is doing. So you have a pure EV lineup from BMW, Volkswagen, Tesla, which is a famous known and newcomer, but also a pioneer in the plug-in hybrid vehicle, which is the Mitsubishi Outlander. Toyota, who is one of the pioneers in hybrid vehicles, now is coming in the plug-in hybrid with the Prius as well. And of course, in the electric vehicle. So, you know, as you can see, we have a huge lineup of electrification, but whatever it's battery propelled vehicle, hybrid or plug-in hybrid, all of those cars have in common electrified powertrain. That means electric motors and inverters and other power electronics like chargers, DC to DC converters, and some other accessories. So this is a huge change, and just keep in mind that automotive is a quite old industry, more than 100 years ago, 100 years industry, and who is facing in a few years more changing than it has faced the many past decades. So the question is, why are we going to all those changes? So there are mainly three main reasons. The first is the CO2 reduction pressure. So this is not a wish of the industry, but this is clearly a regulation. So I just show you here, this is what we have in Europe, but keep in mind that in North America, China, and many other parts of the world, the trend is the same. The regulation would be slightly different, but the trend is to fix some CO2 reduction trend. Actually, this is 95 grams per kilometers in average on sold car, you know, and there's a target to 59. A key point is that there are a huge penalties if you go over that limit. So actually, this is 95 euro per gram and vehicle sold. So keep in mind that for an average car manufacturer who is selling 3 to 5 million cars per year, 1 gram is several hundred of million euros of penalties. So this is not just a detail, okay? So this is one of the main reasons. Another one is another regulation who is on air quality. So actually we have Euro 6, I would say in Europe, or this is the same for other part of the world. But all those regulations slightly decrease the exhaust gas level, all pollutants, so NOx and so on. And this is a huge constraint with request. Right now, we cannot, we will not be able to, for example, to fulfill Euro 7, which will go in the coming years, without any, at least a small electrification, would say in 48 volts, okay, because it will require a lot of power to have a thermal management of combustion engine. And by the way, that will increase significantly the global cost of the powertrain and make it an advantage to the electrified one. So this is really a huge technical constraint that we will have to face. And the third one, this is not a regulation, but also something we have to face and have a deep look. This is the global access restriction. So this is, I would say, more local incentives. For example, you know, I show you here a map, maybe it's not really up to date in Europe, where you will have some access restriction in big cities. So diesel ban, maybe all combustion engine ban in the town, low emission zone, and so on. So this is something we have to deal with. We also see more and more social pressure that population and mainly in cities says, I don't want to see so much pollution, noise, and so on. And we have to take into account. And this social pressure generally is pushed also by media and influencers. Okay, so I show you here on something, the green NCAP, C40 cities and so on, who are in that view of access restriction to standard combustion engine car. So this is main reason why we have to make this huge change and very fast change to move to car electrification. And so now let's have a deeper dive on how it is done. So of course I have just a few minutes to explain, so it will just a wrap of what it can of a global functioning. So first of all, you will have here a battery stack. Okay, so of course with many hundreds of cells in general, or tens, with main switches, okay, to to disconnect the battery when you don't need, typically when you're apart, and also a control electronics, which will go with a battery management system that measure the voltage of all battery cells to give you information on how they are charged, the temperature, the state of health, and so on. And all those information via a network, generally a CAN bus, are sent to a supervisor that aggregate all those information. This information also comes from all other parts who are connecting to a high voltage network. So battery charger, isolating DC to DC converter, who is acting as a standard alternator that you can have in a classical car to supply in energy at low voltage, 12 volt network. And I show you here also all what we call a junction box. This is something that split and distributes the high voltage to all consumer that needs high voltage. So I make it here in orange, because if you look under hood of a car, this is the color of the connectors and the cable. So when you see something orange, say it's high voltage, okay? Another key thing to keep a fault tolerance, all the high voltage network here in orange is isolated from chassis. That means that's like if you know for a distribution network, the IT mode that allows you to function with the first failure, mean an insulation failure on the cable, whatever. So you will have bring a high voltage potential to the chassis, but it's isolated, so you can continue to work. You will have an orange light on the dashboard to say you can run again for a few minutes or hours, but go to the garage and make the right maintenance. Okay. Just to finish, this is the classical architecture. Of course, you can have multiple e-motors or inverter. So this is typically classical for hybrid vehicles, or sometimes when you have a four-wheel drive, you know, for Tesla, you have it's a real propelled car. but you have an option to have a driving on the front wheel, on the front wheels, and of course you will have a rear motor and a front e-motor that helps to have more performance. Important things, all electronics devices have their own regulations. So I mentioned that you have a global supervisor that is discussing via a CAN bus to all devices that have their own local hardware to control locally all devices on the high voltage network. It means inverter, DC to DC, chargers, and so on. You can have also many other devices connected to high voltage. And just to finish, you will see in the literature generally BEV means battery electric vehicle, so coupled only by battery. HEV, hybrid, so combustion engine coupled to battery and electric powertrain. And PHEV, this is the same but with a bigger battery and a charger that you have more autonomy in pure EV. Okay, so go in deeper on how does look the inverter. Just keep in mind that power electronics is the key to control energy flow. So basically, this will be the key, for example, in electric powertrain, to apply a torque request to an electric motor. So you press the throttle and you say, I want a specific torque on the wheel. And this torque will be controlled by the power electronics. So I show you here the basic schema. I don't know if you still have seen such kind of things. The main thing you have to keep in mind is this is made with high voltage semiconductors. Okay, and a key point is that all those semiconductors are working in switching mode, on or off. Okay, so the main reason is that to limit the losses, okay, the conversion losses, because you have in general tens of kilowatts, maybe hundreds for bigger ones, and of course you have to have an efficiency of over 96 to 98%. So you clearly have to take deep care to do not dissipate in the semiconductor, and for that, this is for sure the switching mode. So what does that mean? For example, I show you what would be a voltage among phases here, that you the shape of the voltage that you will bring to the winding of the electric motor. So for this, you can see you have a fundamental, which is a sine wave that you can control in amplitude and frequency, and that will help to control the torque, the speed, or whatever you want for this electric motor. A key point is that this high frequency switching that will request specific digital techniques to bring this switching pattern, okay? So just going over. What does that mean first on the hardware? So I told you at the beginning, you have a supervision software that controls all the electric devices of the car. So basically, you have the throttle position that requires the driver, that gives information of the pressure you apply to this software. you have a filter that translated in a real torque request to the inverter. This is, of course, taken into account from other devices, typically BMS, to be sure that the battery is able to deliver the request torque or power, and so on. And this torque request arrived to the local control of the inverter. So you will have first a regulation loop, so who is typically the that follows the classical regulation techniques. So that will be looped by different measures, phase current, rotor position or speed, limitation with temperature to make sure you don't have over temperature. And by the end, that will give you a voltage request to each motor phase. And another specific module, which is clearly due to the working in switched mode of the power electronics, that will give a modulation strategy to give in real time all the on-off signals for each switching devices. And in terms of hardware, you have a free strategy. You can have all executed by a single controller. So in most of the time, this is done in a DSP core with a lot of I/O around. So of course, analog inputs and a specific logic controller that can give you a specific modulation. If you want to have a more specific modulation strategy, you will have, of course, a processor that is running regulation loop and make it this in another hardware, specific logical programmable hardware, so FPGA. I don't know if you're familiar with it. A field programmable gate array. So this is typically something that you can program with a logical mindset, let's say. And of course, if you have a large diffusion of that hardware, it can be possible, I would say financially interesting, to have a fusion of both functions. So in the same device, a controller and a logical device programmable in the same circuit. Okay. And just to have a small explanation of the modulation strategy for switch device. So something quite known as pulse width modulation, PWM. So how to translate a continuous value into on-off order for each switch. So I just show you a basic circuit as an example. You have, imagine here, it's battery voltage, you have a load where you want to just give to this load a fraction of the voltage. So you can have two positions. The first is here, you have the full voltage in that field on the load, or you have a freewheeling here, so you have no voltage. And of course, you cannot turn on both devices because you will short circuit the battery, or have a full open circuit. This is only possible when you have no current, because in general the load is inductive and you cannot cut off the current in an inductive load. So by considering those two states, we have a freedom left by what we call the duty cycle. So that means the ratio between this time and this time. That allows to change continuously each period. So just to make you a rough sketch for how it works. So for example, you want to give that average value, you will apply this kind of duty cycle that will give you this value. If you want a bit lower, you will reduce the duty cycle, and lower again, you will reduce again the duty cycle. So this is a quite simple example just to show the technique. Of course, beyond that, there are existing many variations of those techniques, so who have been developed mainly on application needs, and there's a quite abundant literature available, so you can have quite many information and go deeper in those techniques if you want. Something important for control that I would like to mention, beyond the useful signal. So I show you here a sine wave and its PWM modulation. So you can see that, of course, if you have a look on the harmonic spectra here of this modulated signal, of course, you have this sine wave here. So that's, of course, the minimum. But you will have here, of course, many harmonics due to the switching pattern. Okay, so what does that mean? That means those modulation strategy are clearly linked to filtering strategy. Okay, so here you can see you have here a zone when you don't have any harmonics. So this is a zone when you can place your filter to reduce as much as possible those harmonics. And this filter has to be taken into account in your regulation loop, okay? So I would say, for example, this filter can be specific devices that you add in your circuit. So I show you here, so I just redraw the inverter here that will have what we call a DC link capacitor. So this is a specific device to act as a filter. And there are other devices on this side that will have a function for filtering. That would be impedance of the cable between battery and inverter. And of course, the series impedance of the battery. So this is, I would say, three elements that will act on filtering. And on the other side, for electric motors, you will have no more filter design except, of course, for the current, the impedance of the stator of the motor. Okay, so which is quite highly inductive, and that's enough to up to now filter the current despite the highly sharp voltage that you send to the electric motor. Okay, so really keep in mind that all those harmonics due to the switching pattern, which is mandatory for power electronics, needs to take in account filter design as well, and take this filter impedance in the transfer function for control. And just as a takeaway for you, I think a key point is to keep in mind that electrification of powertrain for automotive is a major trend for the coming years. There will be no major manufacturer that could escape to that. This is the case for everything. And I would say keep in mind that for an old industry like automotive, this is a very deep change. We will face in the coming year more change than we have faced in the several past decades for many things, engineering, manufacturing, maintenance, and so on. Another key point is that power electronic is mandatory to control electric energy flow, and for that reason, it is mandatory. It goes with the electrification of powertrains. Okay, so we don't see it so much, but power electronics is a key part on EV or HEV, PHEV. Okay, because there are many devices who have power electronics. I mentioned inverters, but this is the case also for battery charger, DC to DC converter. You have AC compressor for thermal management, who is in general electrified, and many other accessories. If you can have anti-roll systems or chassis control that request electric actuators, and by the way, power electronics. So keep in mind that power electronics has been made, I would say, automotive took sometimes to adopt power electronics. Now it's the case, and it's a really key aspect for future powertrains, future cars. And the last, the control of power electronics gives specificities, and due to this high frequency switching pattern. So you know that you can have many derivatives for modulation strategies. You can act at very stretch real time. Let's say this is typically 10 to 100 microseconds sampling time to make the local regulation. Sometimes it's shorter. And to finish, keep in mind that those modulation strategies requires filtering device that have to be taken into account in the regulation loops. So, and also among devices, you know, you will have, just to say, in the filter of an inverter, which is one of its main goal, but you will see part of the input filter of other parts who are connected to the high voltage network. So the stability of the global high voltage network inside the car has to be really taken into account. And just the last slide on the future trends, because the story doesn't stop as it is. So for power electronics, what we can say in the coming years, one of the main change would be the adoptions of what we call wide bandgap components. So actually the power components are based on silicon, mainly for high voltage IGBTs, or power MOSFETs when you want to have high frequency. Actually, for inverters, the main change will be to change from IGBT to silicon carbide MOSFETs. That will lead to a much better efficiency and also a smaller volume. So the main aspect for wide bandgap components is their ability of the material to work and with a much higher electric field inside the material. And by the way, to get a smaller device. So just to compare here, this is silicon superjunction. This is something you have in battery chargers or DC to DC converter, where it's specific resistance, so on-state resistance around 1 million centimeters square, where its counterpart in silicon carbide is around 4. So this much smaller. Another technology, another material that will go into, this is what the GaN, so gallium nitride, so which is a bit higher bandgap as well. Actually, this is lateral devices, and which will be mainly for high frequency conversion. So let's say mainly DC to DC converters and also battery chargers. And I just mentioned here, maybe that will be, but let's say in at least 10 years, a killer for low voltage SiC MOSFET. This is the use of GaN, but vertical device, but this is actually on academic research. And the second main future trends you will have at system level, this is the battery charger reversibility. So that will help to use the battery of the car when it is plugged as a storage, not only now to evaluate it to move the car, but to help to exchange energy, and by the way, leading to reduce the cost of ownership of the battery, reduce the carbon footprint of the use phase of the car by helping the development of renewable energy, which are by function intermittent. So there are many additional business that can be done with this. You will see that if you have a large diffusion of electric car, that will be a key aspect for storage, for smart grids via what we call vehicle to grids. And this will go much over than to sell a car and to run it. Something that we will see also, it's a network pre-charge, so to have a DC to DC converter reversible, but it's not so big. And also, this is, I would say, a story, basic story of automotive industry, is to share resources among all parts and via a standardization of interfaces. So basically, as I told you, for example, to share filters among the multiple parts, and that will be much more easy with small parts that will be brought in the same box, in the same, I would say, huge power electronic functions. So I think I'm a bit over time. So that's the end, and I would be happy to answer your question.
Okay. Yeah, thank you very much for your nice talk presentation, Serge LOUDOT. It's very, very interesting. Yeah, there is some interesting topics about power electronics and what is the future of this power electronics on electrical, on e-mobility, and so on. So thank you so much.
You're welcome.
Any questions? I think you have many questions to ask for Serge. So who can start?
I can start, Professor.
Okay. Okay, Ivan.
My name is Ivan. Ivan. I have a question concerning about the lab. Of course, the classic approach. No, I mean how we usually show power electronics, just 6 inverters. No, I mean IGBT. Yes, switches. But what is the reality now? How many layers do we use? And what is the amount of inverters within one phase, let's say, a 3-phase system? I mean, they're in cascade, layers, series of. If it's not a secret, of course, for you know.
What? Excuse me, just.
This one, yeah, this one.
Here, yes.
No, next. Maybe next.
Okay.
Next. Here, yes. We have switches.
Yes.
IGBT switches.
Mm-hmm.
And I know that for smoothness, we use them a lot in cascade, maybe 4 or 5 layers to make it smoother, the sign-off.
Yes, you can have multi-level devices.
Yes.
You're
and
right.
what is the amount of levels now? But this is interesting, yes.
Yes, that's possible. Actually, as far as I know, we don't expect of that for 2 reasons. Because there are different ways to have a multi-level inverters. So with flying capacitors or with a clamping neutral point. In any way, this requires additional component, passive component, that it makes it bigger. So what we saw is that the balance between the lower filtering request compared to the additional passive components is not in favor of the multi-level inverter. For this application, I mean, because typically in automotive, the voltage of the battery is maybe 400 volts. In some hybrid device, you are to 200 to 300 volts. And for high-end car, like the latest Porsche Taycan, you go up to 800 volts. But this is fully compatible with the actual semiconductors. And that would be possible, but definitely there's no interest for this application. That wouldn't be the case, for example, if you want to go to higher voltage. So for a specific industry device, when you go to a few 1,000 volts, that would be clearly an interesting point. But today in automotive, we don't see the benefits to go in that way.
Thanks a lot. Yes, and one more small question, just interesting then. What is the biggest challenge right now for the power electronics in Renault, let's say? What you see in your department, the biggest challenge? If it's not a secret, of course.
If I would just repeat what I hear of my boss is to reduce the cost. You know, because there are many power electronics device. Just to remind here, so you have here, and some where you have some electric motors and other here. So the cost of power electronics is the second on the podium, I would say. Of course, the most costly part is the battery, and second is power electronics. Third is electric motors. Okay, so that's clearly a key point. Over that, I would say a challenge would be to also add additional value. Typically, that would be to increase efficiency. This is really a key value to have most efficiency for inverter, for example. Actually, you can see in some papers that moving from IGBT to silicon carbide MOSFET will help to increase 2% almost on a driving cycle the efficiency of an inverter. That means you will get some additional few kilowatts hour of energy free to move the car and not to dissipate in heat in the inverter. So if you make the balance with the cost of a kilowatts hour of a battery, that's something really important. Okay, another key point is also what we saw is the energy efficiency of the battery charger. And also if you use a reversibility, so for example, you have a charging from renewable energy, so you charge, and if you don't have enough energy, you are able to store energy and to give back when you have a lack of production. So this discharging also requests a huge improvement in terms of efficiency of the conversion, and that wide band gap will help. That will help a lot. Okay, and just to finish, also here, you know, for DC to DC, efficiency is also a key point, because you will have typically the power flow is around 2 kilowatts, and 2 kilowatts, this is not nothing. And if energy savings in that field are also welcome. So this is something, a key point that requires to go from combustion engine, where there are a lot of energy waste. Most of the energy goes in heat, and well, it's also always good to save energy, but in a small range. Here, you will have to live with much less stored energy than in a liquid fuel, and you will have to manage as much as possible, the best as you can, this energy. So clearly, efficiency is a key point. And to finish, also a volume. One of the key selling point for electrified powertrain is to possible ability to reduce the volume, and for a same-sized car to give more space for passengers and useful space. Okay. And this is also a key value. So that's why more and more we make dedicated platform for electrified cars, because when we take the I'd say combustion engine platform that we electrify, we have all the constraints of combustion engine platforms, so that gives you not this freedom space. So that was clearly a key advantage, for example, for Tesla, that started from scratch and don't mind of the past 100 years past of combustion engine powertrain, and they started to a platform only dedicated for electric vehicle, and that helps a lot in terms of weight reduction and giving better usable space for passengers.
Thanks a lot, Professor. Yeah, it's really interesting, because I will think more about noise and that one, but of course we are we are selling cars, so we need
yes,
more thinking about the cost and efficiency than about noise and maybe some smoothness.
yes,
So okay,
yes.
yes, it's right, definitely.
Yeah, you
Thanks a
have,
lot for your
I would say,
explanation.
noise and also torque at low speed, so huge
Torque
acceleration,
ripples, yeah.
and of course that's quite well known.
Okay, thanks a lot.
Yeah, so I agree totally with your answers, Serge, Ludo. So just to go back to the questions about multi-level inverter. Yeah, I totally agree with you that it is not interesting here because the voltage is not so huge. So I understand the issue, but maybe there is a need in this application of electric propulsion when you have failures of power components, or when you fail one leg of the inverter. In this case, what is done in this area? If possible, to say some words about this.
Okay, so I think the fail-safe mode actually, so when you have a three-phase inverter like as it is, when you lose for example here a switch is off or whatever, of course this is you have to stop. You don't take anymore. So this is one of the biggest failure we can have. First thing, mainly for inverters, what we focus on is to keep the control of the torque, because this is a question of safety. You know, you can have a sharp change of the torque that could that's not predictable for driver, and of course that has a big safety impact. But to explain, up to now, losing something in the inverter means clearly you stop and get on the side of the road. We could manage to complexify the topology to be more fail-safe. But today, what we have a deeper look is more on the technology. So to make sure that the technology, so I would say interconnection or of the, let's say in general, it's a 6-pack power module, to make it reliable or to prevent any failure during manufacturing. And of course, we can imagine, it's not the case yet, to make a diagnostic, online diagnostic, if there's a risk of failure. But right now, clearly, this is more done to manage reliability and production quality. And we have, let's say, almost 10 years of experience, and mainly with the electric vehicle. And it works. What we saw, it's not so much a failure in power electronics. Most of the cases are failure outside, mainly insulation in electric motors or things like this. So that's it. But just I would like to underline things. Globally, the reliability and the availability of electric powertrain is quite high, and in many cases much better than combustion engine that we can see, even if we have produced them for decades and decades. But you're right, if we have a failure in power electronics, you stop the car. But this actually, this is not so important in the feedback we had for the last years.
Yeah, thank you.
Thanks a lot.
Thank you so much. So we have 3 minutes remaining, maybe for last question before going to the next presentation.
Yes, Professor, I
Yes.
have a question.
Yeah.
Yes, I have a very short question. Professor, can you turn the slide to the last page, the last slide?
Yes.
The future trends. Yes, not the, yes, this one. And I'd like to know in the future the trend of the battery is what I mean is to develop, is to try to find some new materials for the larger efficiency or the larger capacity of the battery, or we can like to change the battery or to replace the battery in the station. I mean, now we have 2 ways to choose, and I'd like to know now what is our focusing for Renault now. Yes.
This is a very good question.
Yes.
I would say there's no simple answer. You know, we experienced a few years ago what we call a quick drop. So to increase the availability of a car, because the electric car spend a lot of time while plugged and not available because the battery is empty. So when you go, and there's also a robustized system that take off the empty battery and to put in another one, and you go, it took a few minutes, and so that was more or less like a liquid fuel for combustion engine. So the idea was interesting, but economically it didn't make sense, because you have to the quick drop changing station was quite really costly. It requests a huge standardization of the battery pack and a storage, so to a management to don't keep to store too long time a battery inside the changing station. And also it requests for this to have a fast charging chargers inside the station, because it's important to, when you take off a battery, to put it in the field as short time as possible. So that's the first point. And now the trend is more to use or to focus on fast charging. So just maybe I just show you where it is. Here you have a plug, so this is for AC charging, and you have big plugs here that is for fast DC charging. So you have an external charger, and right now maybe you're aware of Tesla superchargers. So as you can see here, so the order of magnitude is between 100 kilowatts to 250 kilowatts of instantaneous power. So that makes quite a huge power and low charging time. But this brings quite some overcost for the battery pack, because you have mainly for thermal, you have to cool the battery pack. The easiest way is to have a low power charging, and the battery pack cool itself naturally during its charging time, that will take a lot of time here for Tesla, Porsche Taycan, and so on. So those high-end cars, the customer wants to have a full availability and the possibility to have a fast charging. So in a few minutes, you get the full energy, but it gets a very high overcost. Okay, so this is possible, but it will remain for high-end cars. And for other, I think, all more standard, I would say more affordable cars. The trend will be to have medium power charging, who is, let's say, 32 amps, single or three phase. So you will get with that around 200 kilometers of running range for 1 hour of charge. More or less, this is this. And with this, you will have quite good balance, economical balance. I would like to focus on another point for the battery is the raw material. You know, I would say this is definitely for me the main challenge. As I mentioned here, sorry. Would like to hear the social pressure. We can clearly forecast a huge social pressure concerning the raw material of the battery. So that means we have to take very care of what we are using. One of the top level one to have a deep look on is cobalt, because this quite not so available. And for the social responsibility of the company, we know that it has been extracted in quite very, sometimes very bad social aspect. You know, it comes mainly from Africa. There are some forced workers and so on. So the goal would be to remove cobalt from the battery. This is possible, but you have to make some, let's say, compromise with the full performance. I would say power density and so on. But this is something we have to deal with, and also recyclability. So we have to design the battery to be fully to recycle all the components, and develop all the manufacturing and everything to make this recyclability effective in real life. So I would say, just talking for Renault, what we are doing is, when battery is out of France now, the warranty is for almost 8 years. And we say the battery is, when you lose 20% of state of charge, the battery is over for moving, but it still have a value in static position. So what we are doing, we are getting this battery to make it in store, what we call storage tower, to help renewable energy. So it helps when you have solar plants or wind power and so on, to stabilize and give them also an average power. So that's a point. And after that, when it's fully over, we have to fully recycle the battery. Okay, so keep in mind that we can have the full performance, but in our concern, the main challenge for the battery will be the global life cycle of the raw material. I would say you have we faced Dieselgate, and definitely we have to be very careful, and this is possible. I think we will succeed, but anyway, this is a challenge for the management of the battery and mainly raw material.
Okay.
Okay, thanks,
So,
Professor.
Yeah, thank you again, Serge LOUDOT. So I think,
You're welcome.
yeah, we have to switch to the next presentation. So thank you so much for this presentation about mainly power electronics and what is done on the e-mobility, and particularly in the Renault Group. It's very, very interesting to interact with you about these issues. Thank you, sir.
Thank you.